okay, I have some phenomenon, I have some set of phenomena,
Hmm.
and I create a neural network which is able to predict the n
Yeah.
plus one like element.
Yeah.
But the neural network itself is not particularly explanatory, and it doesn't tell
Yeah.
me that much. It's just a set of numbers, basically. Or
Yeah.
does that make
Uh,
sense? Mm.
I've also
Mm.
had this debate both with myself and with other people many times, and kind of the conclusion I've come to is that neural networks can be very, very good engineering,
Mm.
but in that sense, they're also very,
Mm.
very bad science.
Okay.
Um, they can be very useful for, detecting certain events. People have done great work on using neural networks to detect certain types of particle events in particle accelerators, things like that. Pierre Baldi's group has done very interesting work there, and there it's essentially scaled up statistics. But actually, that particular use case, they're saying, all right, the theorists come up with a new proposed particle, then you run tons of simulations, and then you train a neural network to detect what those events would look like. So there you already have a potential explanatory theory, and the neural network is used as a kind of sophisticated sensor for telling you whether that theory is right or not.
Okay.
And when you're trying to learn a neural network just to do prediction, that is, I think, a lower level of explanation.
Right.
And I think for industrial applications like speech recognition, image recognition, where you're not trying to come at an explanatory theory, you're just trying to build a product that works. That's fine. That's great. If that's what's the most efficient, use it. Go for it. Cool. If you're trying to come up with a theory of how intelligence works, I don't think training a deep neural network is the end of the story. It can be a step on the path. And one interesting trend in neuroscience and psychology today is training these deep neural networks to do cognitive tasks or to do neural tasks like object recognition, and then going in and using this as, again, a computational model to experiment on in a way that you can't experiment on in a physical system. Go in and probe it and sort of tweak parameters and do sensitivity analyses and things like this to try to figure out what features this thing is responding to,
Right.
as a way of possibly motivating more simple, elegant theories later on.
Okay. Yeah. This is the
But I don't see it as the end of the story. Some people might be happy just with, okay, if we have a neural network that can do everything that this particular animal's brain can, this, the nematode worm is solved if we just have a dynamical system that does everything that it does. And I don't think there's more than just data fitting. There are deeper levels of explanation.
Right. Which then gets into the super philosophical stuff of what
Yeah.
is an adequate explanation.
What is
and
an
what counts,
explanation? And that sort of thing, exactly.
But I have seen things that are quite similar. When you learn about neural networks and handwriting recognition and things like this, you always see, these, like when you have your convolutional layers or whatever, and then you have these set of neurons are looking for these kinds of edges or looking for flat lines or looking for this kind of curved shape. So there is that kind of thing, I guess.
Yeah.
And you said that people study. Is that what they're studying, or are they studying something different about neural networks? Are they trying to piece together like which parts of the neural network are looking for which types of things in the images or in the data set?
All of the above.
Okay.
It's a fertile field. There are a few people in particular, Dan Yammans and Jim DiCarlo and a handful of others, who in some pretty groundbreaking work showed that the features of deep neural networks trained for object recognition, the intermediate layers. So you're only optimizing this network to put out good predictions at the final layer.
Yep.
You're not really imposing any constraints except through the architecture on what goes on in the middle layer. Deep neural networks trained so that the output reproduces what the deeper layers of the primate brain do. The features in the intermediate layer better predict the responses of neurons in intermediate parts of the brain than any of the the best theories that, 4 decades of vision neuroscientists have been able to come up with by going in, designing different sets of stimuli, showing them to monkeys, and going in with probes and recording directly.
That's super. So if I
which
read
was,
that,
really interesting.
If I read that in like the news media, I would be like, okay, this is clearly overblown, and people are just sensationalizing a news story.
Well,
but, like, to what extent are neural networks very similar to human brains? Because I was always told that they are not.
Well, it's the sort of thing where the correlation goes from like 20% to 30% or something like that, or maybe 40% if you're lucky. So I'd say until you can exactly predict what the response will be, it's not solved. So there's still lots of room, and I should say this is only predicting the first like tenth of a second of what happens when you look at an object, because there are massive amounts of feedback in the actual brain, and the first glimpse we have of something is often wrong, and our brain is kind of constantly we are constantly updating our beliefs about what it is that we see based on new evidence, or just spending longer staring at whatever it is we see. I mean, the process of seeing something is itself dynamic. You don't just look and then have a fixed representation. You're constantly interpreting and reevaluating what you're looking at.
Yeah.
I mean, you talk to any artist, and they can tell you that the more they work, when they work in different ways, it trains them to see the world in very different ways. So perception is an ongoing dynamic process, which mostly for practical reasons is something that isn't really addressed so much in these deep neural networks, just because it takes a huge amount of computational power to run these things. Yeah. So just for efficiency, you kind of put everything through in one pass, and you can maybe do a few iterations on top of that where you use more sort of top-down information to update what you see. But for most tasks, just having a really big deep network, is the sort of thing that will get your score higher. So in that sense, there is still a very big gap between biological vision and computer vision, but it was very surprising to me, and very surprising to a lot of people in the field, that even these models were still better than, even though we don't really know what they're optimizing for, they still discover these representations that are better than anything the most clever and hardworking neuroscientist has been able to cook up in 40 years. So that was quite startling.
That's pretty interesting. Yeah.